Okay, so it's 7:59. So maybe by the time I finish the introductions, it will be 8 o'clock, so we can start on time. So good morning, everyone. Again, welcome to the 18th PAASE webinar. So the Philippine American Academy of Science and Engineering is an organization of scientists and engineers of Filipino descent. So initially, it was formed by scientists from the US and the Philippines, but now we've expanded our membership and we have members in different countries. So for today's lecture, our speaker is an associate professor in the Department of Chemistry and Physical Sciences at Pace University and an adjunct faculty at CUNY York College in New York City. He finished his bachelor's and master's in agricultural chemistry degrees from the University of the Philippines in Los Baños and his PhD in chemistry from University of at Buffalo. As a researcher, he specialized in analytical chemistry, instrumental techniques like chromatography, spectroscopy, and electrochemistry, analyzing samples of interest in biochemistry, nutrition, food science, and environmental science. He is also involved in uplifting science education in the Philippines through his project Community or Chemistry in the Community, initiative giving free webinars and lectures, seminars, workshops in different institutions. The latest one was very honored with our speaker for the day, Elmer-Rico Mojica.
Hey, thank you very much, Kay, for that kind introduction. So today, I'm going to share to you what have been done in at least the field of Raman spectroscopy. Okay, so the topic that I'm going to discuss today is just what I have done for the last, I would say, 9 years in Raman spectroscopy. So to add some sort of taste in the title, I put there proving dancing molecules because Raman spectroscopy is really vibrational spectroscopy. Okay, so magandang umaga sa inyong lahat and thank you for attending this webinar. So when light interacts with matter, there are several processes that happen. So usually there is a transmission, where's the passage of light through the material without loss of energy. There is reflection, which is the change in light direction at a fixed angle. There's an absorption, which is the transfer of light radiation to energy within material. Luminescence, which is the emission of light by a substance that has not been heated, like fluorescence and phosphorescence. And the scattering, where there is a change in the light direction at different angle. Now, in this scattering, we could say that the scattering can be elastic or inelastic. So we have an elastic scattering when there is a collision between photon, okay, and molecule that results in no change of energy, just like what's happening here in Rayleigh scattering. So whatever the energy that is input, that is the same energy that was what we called return back. So in the end, there is really no change, gain or loss of energy. And we call this Rayleigh scattering. And most of the time, 99.99% of the scattering is elastic in nature, like Rayleigh scattering. That's the basis why the sky is blue. Now, however, in some of the scattering, okay, when there is a loss or gain in the energy, okay, you have this inelastic scattering. And this is the collision between photon and molecule that results in a net change in energy. So if the change is what we call losses energy, so there's a corresponding change in the wavelength here. So you have here what we call the Raman scattering in Stokes Raman scattering. But if there's a gain in energy here, this is the Raman anti-Stokes scattering. And this is the basis of Raman spectroscopy. And if you're going to look at the intensity, Rayleigh scattering is the strongest. Okay, 99.99% of scattering is really Rayleigh. And the less than 0.1 or 0.01 to 0.1% is just Raman spectroscopy. But the change there in the wavelength, that is enough to determine any changes in terms of the vibrational modes in the molecule. Okay, so if we're going to look how Raman really looks like, so I have a short clip here. So as you can see here, you can only see Raman, okay, if you have a filter that will cut out the Rayleigh scattering. So Raman is usually weak. And the story on how it was discovered is really a fascinating one. So as early as 1923, Adolf Meckel already predicted the existence of this inelastic light scattering. And then Landsberg and Mandelstam see unexpected frequency shifts in scattering from the quartz. And in 1928, okay, Chandrasekhara Venkata Raman and his student K.S. Krishnan discovered the Raman effect. Okay, and the discovery that he had here is he was really confident that it already exists, and it's just time that they will discover this thing. But it took a while for this to be revolutionized. But you know, Raman, when he submitted the paper in Nature, they said that one of the reviewer rejected it, but the editor accepted the thing. And in 1930, by early as July, he already booked a trip going to Sweden because he expected to win the Nobel Prize in Physics, which he won later that year. The announcement came in November. So how did Raman discovered this scattering that is named after him? So in his original experiment, so this is the setup that he had. So he used he focused a beam of sunlight and passed this beam to a green filter. So what happened? The green light that was passed through a solution of different liquid during that time, he was able to observe there's some sort of an emission, okay, on the scattering that it has. So using the chloroform, he was able to see that there's a faint yellow emission coming out of the chloroform. So what happened? The green light, which is higher energy, okay, it was elastically scattered by the chloroform, and the resulting emission of yellow light was his proof of the existence of this Raman scattering. And he was able to come up with the first spectrograph, as we call it here, using the benzene. So this is, we could say, the first Raman spectra that was reported during that time. And the basis for this instrument, what we call Raman spectrometer, is still the one being used as of today. So most of the Raman spectrometer, they have this laser as the source of light. And what it do, okay, you're going to focus it, illuminate it on the sample, and it results to scattering. So in that scattering, you will see still the source of the light, and at the same time, okay, the Raman emission. So for you to be able to separate the Raman emission, you're going to pass it back through a dichroic mirror wherein only the Raman emission will be collected. So it will be collected in a charge-coupled detector, CCD, and from that, you will be able to see the Raman spectra. And together with the IR, they are known as what we call the vibrational spectroscopy. Because what they do is they look at the vibration of the molecule. That's why I call it the dancing molecules. Now, both of IR and Raman, they can be classified as vibrational spectroscopy. But the thing is, the information that you'll get is complementary with one another. Okay? Because what happened, although they both involve vibrational spectroscopy, the principle behind the transition is different. Okay, so for IR, usually it depends in the change of the permanent dipole of the chemical bond or molecule with the vibrational normal mode in order to produce absorption. So there is absorption in the IR for the material to vibrate. So we could say IR absorption is a direct resonance between the transition frequency and photon frequency. Now for the Raman, okay, it depends on the polarization or change in the induced dipole to produce Raman scattering, as the one that I called earlier as the inelastic scattering. So what happened? I hope the noise. So it scattered the radiation shifted from the incident laser frequency by vibrational transition frequency. So those vibrational frequency, that is already the characteristic of chemical bonds or group of bonds in the specific molecule. And this shift of vibrational frequency, these are sensitive to the local environment of the molecule, such as the crystal phase, the local strength, and the level of crystallinity. Okay, local strength and degree of crystallinity. So this is the basis of the Raman spectroscopy. So if we're going to compare an IR and a Raman spectra, this is how they look like. So some peaks you see in IR, okay, that you don't see in Raman, and some peaks you can see in Raman, but not in the IR. So the best thing to what we could look at vibrational spectroscopy is to utilize both techniques. But between the two, IR is the more popular. There are only few people doing Raman. Okay, and if you're going to look at the Raman application, it is useful in pharmaceutical industry, especially in API, the active pharmaceutical ingredients. It also detects the polymorphic forms of the different drugs. In biomedical, it checks on diseases, proteins, and DNA, and I have one example on that in my presentation today. In material science, it detects the local strain, the lack of crystallinity, and sometimes the heterogeneous nature of the material. And in terms of nanotechnology, it's been used to analyze the nanowires to understand their structure. In terms of forensics, it's usually used. I don't know if you heard the Batman movie Massacre in Colorado. When they tried to check the house of the suspect, they use robotics that contains Raman spectrometer to determine if there's some explosive at his place. And then you can use it for gemology, geology, and mineralogy. So if you want to look at the gems, so sometimes if they want to determine if it's fake or not, Raman is a very good technique. And then in archaeology, if you want to detect forgery in paintings, you can use Raman. And I have some guests at my lab who's using our instrument to check, okay, some forgeries in the museums around here at New York City. And the good thing is it was used in one of in the Mars rover. They call it the Sherlock, the scanning habitable environments with Raman and luminescence of organics and chemicals. So what this Sherlock has, it uses spectrometers, a laser, and a camera to search for organics and minerals that has been altered by watery environments and maybe signs of past microbial life in Mars. Okay. Now, there are several advantages of using Raman. You can use it at all physical states of sample. You don't need sample prep. The spectra from each material are unique, and you can use it to identify the materials conclusively. Just like IR, it's non-destructive. You can always recover your sample. You don't need any vacuum when you do the analysis. It's a rapid analysis. Okay, although if you want to improve the signal, you can always collect more signals on it. It can work with aqueous solution. I think this is the main advantage of Raman compared to the IR. Because IR, if you have the water, you have the hydroxy bond there that forms a broad band around 3300 region. Okay, so that's one advantage of Raman. Glass vials can also be used. Another advantage for IR, you need to use the cells. Okay, and for remote sensing, they now develop these fiber optic cables. Okay, now the disadvantage that you for this Raman is you cannot use it for metals or alloys. The Raman effect is very weak, but you can improve it. There are ways to improve the sensitivity of it. And you cannot apply this in fluorescent sample. You're going to have some problems if you use samples that are fluorescent. And if you have also samples with color, it may absorb the laser light and it burn. And I have experienced the thing. And one thing is it's a little bit more expensive than IR. That's why it's not really being used more here compared to IR. Okay, so what I'm going to discuss today is what I did with Raman. So I'm at PAASE University. So this is a private non-sectarian university here in New York City where I have, but this has a campus near Westchester, which is a train away from the home place of the Clintons, the former president and the Secretary of State. And it's easy to see our university. So if you're standing Brooklyn Bridge, so there's our university being dwarfed by the more famous spiral building, the Gary building that we have here. Okay, so we're near the City Hall, we're near the Wall Street, and we're near the former World Trade Center. It's a heritage right now. So I have an active research group that is made up of almost undergraduate students. And we always call ourselves the team, okay? And we always joke the meaning of the team, which is just Team Elmer-A O.E. Mojica. So we said, if the students like me, you could say it's awesome. And if the students don't like me, there's also a 7-letter word that has the A, N, O, and E on it. Okay, but what I usually do is I ask my team to work together because I always say together everyone achieves more. But before I went to what we call the PAASE University, I already mentoring students before, even before I took my PhD here in the US. I have an active undergraduate research in UP Los Baños. And then I just continue what I was trained to do when I was there. So as of now, I have 87 students who directly learn from me in one way or another. And of that 87, 54 came from PAASE University. And the research that I have is usually instrument-based analysis. So I usually have experience in one way or another in the trifecta of instrumentation: spectroscopy, chromatography, and electrochemistry. So what I'm going to discuss tonight is part of spectroscopy. And the italized thing that we have here is the one that will be included here. So I have worked with proteins, sol gel, phenolics, food science and nutrition, environmental samples, and then pharmaceutical antibiotics and some nanomaterials. And in addition to that, I also have some experience doing computational chemistry. So here I just use the software, okay, to bring some theoretical aspect or perspective in some of the instrumental or experimental based projects that I have. So the background that I have with Raman, when I moved to New York City in 2011, so a common friend of mine, a common friend of us, both of us coming from UP Los Baños, introduced me to a Filipino who is based in York College. So that's the first time I used Raman. And I would say this is for now the second newest technique that I learned. And during that time, I'm an adjunct working around New York City. And then in the fall of 2011, PAASE University hired me as a lecturer. So from PAASE University, if I have time, I go to York College to do experiment, to the point that I learned how to sleep in the subway station. So if I need to sleep while sitting, I took the J train. If I have to do it by sleeping or while standing, I have to take the mass passenger taking the 6 and the E train until I come to have my own portable Raman spectrometer. So the first thing that I have there. So this is usually the university or colleges that I work. Okay, I just don't have a picture in front of Pace University. So this is one of my collaborator who went to me to visit from time to time. So the late Alonso Gabriel. So this is my life that I have during that time. And when I was in the Desamero group, Dr. Ruel Desameros, I was introduced to two Raman, and the way that we call is the small Raman, which is this one. Okay, so this is from Yasko, and then we have a modular one that we call the big Raman. So this is a modular one. So he assembled it out of the pieces that we had, and he used a laser base in both of these things. So that's my first, we could say, experience in using Raman until I have my own Raman, portable Raman in Pace University. And when I was able to get a grad student to work with him from the Philippines, he able to add another laser line, but using the same instrument for the Raman. So from the 488 argon lamp, he was able to what we call a line that's around 544, I think. And then in addition to that, he also purchased another Raman, the UV Raman, which until now have not used itself. Okay, so in his lab, there are more instruments than people. That's why I always go in his lab, even though I'm already full-time in Pace University. And today I'm going to describe to you the studies that I have done in Raman. So the first thing that I work is in this so-called amyloid formation. So amyloids, this refers to abnormal fibrous extracellular proteinaceous deposits found in organs and tissues. So usually amyloids, they are insoluble and dominated by beta sheet. So when you have an amyloid, usually, okay, that is associated with the so-called neurodegenerative disease like Parkinson's, Alzheimer's, and everyone's favorite, diabetes. Okay, so what I did is we try to look at this peptide known as amylin, which is co-secreted with insulin. So we could say this is one of the peptide that is responsible for diabetes. So what we did, okay, we look at the chain. This is a 37 amino acids, and we look at this peptide sequence here. And what we do is we prepare it in the lab, the peptide, okay? And we just altered the phenylalanine in this NF-GAILSS. So what we did with the phenylalanine, we replaced it with some functional groups, okay? So what we did here, instead of H that is in phenylalanine, we put a hydroxyl group there, a methoxy group, an amine group, and a methyl group. So those are the electron donating group. And then in another set, we also do some electron withdrawing group. We have the nitro group here, the fluoro, the cyano, and the pentafluoro, where everything was replaced by chlorine. And what we do upon synthesizing, we look at its behavior, okay? If we put it in Tris buffer. So what we're trying to do is it going to aggregate? So if it aggregates or precipitate, there's an amyloid formation. And we try to characterize, okay, the peptides that aggregate. And we use Raman as one of them. So based on the results, all the electron withdrawing group substituent, it assists the aggregation, and all the electron donating group substituent, it prevents the aggregation. So what does it mean? Okay, we're trying to find a way if we can develop inhibitors in the amyloid formation. So if we can inhibit the amyloid formation, it is a good therapeutic, what we call the solution for diabetes. So the one that contains the tyrosine, the hydroxyl group in the phenylalanine, it doesn't form any aggregates. Okay, unlike the one that is the electron withdrawing group. So what tells us that there's an aggregation aside from the presence of those solid particles? This peak at 1670 wave number, because this is indicative of the beta sheet. And then we also have this peak around here, which is indicative for the aromatic ring. Okay. Now we didn't able to see it in the electron withdrawing group. So that means they didn't undergo aggregation. Okay. So whatever we do, we cannot find the ring there. We cannot find any beta sheet. And then we also try to look at some of these functional group that we use. We ran the same sample since it is non-destructive in IR, and we're able to get this peak at 1628 or around 1630, which is indicative also of the beta sheet. Okay. Now, what we're trying to do is what's really happening during that time. So this is the peptide before it was dissolved in Tris buffer. So as you could see, you cannot find any peak in this region, which is indicative that there's no beta sheet. But once it aggregates, you form a peak at 1674. Now for the ring modes, we observed that there's a shift from 1608 going to 1605. So that means tell us that there's a change in the environment within, okay, the peptide. And from 1356, the nitro group shift to 1351. Okay, so we're trying to look at about the pi stacking, the pi-pi interaction. There's a specific type of intermolecular attraction that is unique for aromatic ring. Okay, and then we also notice that among the peptides that we have in our batch, okay, the cyano takes a while to aggregate. I think we observed the aggregates after 2 or 3 days. So when we look at, when we monitor what is happening there, so before the aggregation, we have a peak at 2,251 wave number, and then starts to shift to 2239, and then it starts to shift to 2234. So what happened here, as it aggregates, the environment around there becomes non-polar. So that's the story that we have. And during that time, I'm already getting full-time in Pace University, and I told Dr. Desamero, I cannot guarantee my time with you. Anyway, you don't pay me for anything. So the grad students took over the project, and he was able to develop some inhibitors out of this. But this is the starting point, because out of this, Dr. Desamero was able to get an NIH grant to fund the grad students. Okay, but I still have a lot of data with me that we have not published. So we monitor in time what is happening with cyano, because cyano is a slow aggregating process. So if we're going to look at this at the beginning, before the aggregation, it's here, and then it starts to shift, okay, to a lower wave number. Okay, and then I also look at those fluoro-containing NF-GAILSS. Compare it with phenylalanine and the one that has a lot of what we call the fluoro, the pentafluoro. So we could see here the difference for the pentafluoro. There's a peak here. And as you remove the hydrogen and replace it with fluorine, you see this peak here getting smaller until it's gone when all of the hydrogen in the ring is replaced by fluorine. The same thing that happens here. And then instead of NF-GAILSS, what we do is we replace the phenylalanine with leucine, and we found out that it's still going to aggregate because our suspect before is the ring has something to do with the amyloid formation. But we were surprised that even if the ring is not present, the peptide will still aggregate, as shown here as a peak at 1670, which is indicative again of the beta sheet. So that's the story that I have for this amyloid formation. It was interesting, and I'm also doing something about that, although this is more not Raman related. I'm trying to look at some inhibitors for this, what we call amyloid formation in amylin. And the next story that I have there, so during the time I was at York, they have a MALDI instrument. And one of the matrix that they use is the cyanohydroxycinamic acid. And I was always fascinated with cyano. So cyano is unique because you can find it around the 22 to 2300 region. So what I did, because I have all the leeways to do any research in the lab, is to compare the derivatives of cyanohydroxycinamic acid and then to answer the question, why is it effective as a matrix for MALDI while its isomer is not? Okay, so what I did is we look at all the derivatives of the cyano. So the cyano 4 hydroxynamic acid, and then we ordered the cyano 3 hydroxynamic acid. We cannot find cyano 2 hydroxynamic acid. So what we did is we use instead the one that doesn't have the hydroxyl group, the cyanocyanamic acid. And then the other one, the one that doesn't have the cyano. So we just have like an assignment paper. So we just compare the 4 cyanohydroxynamic acid derivative. And from that, we were able to come up that there's really a difference, okay, in the Raman of these 4 derivatives. But what fascinates us is at the 3300 region, the 4 cyanohydroxy acid has this sharp peak that cannot be observed in the other, what we call derivatives. Okay. So that's the basis that we have for another study. And then we look at the cyano region. So it is expected what we have, the kumaric acid doesn't have anything because it doesn't have cyano in its molecule. Okay. So the next study that we did is, okay, let's compare 4 with the 3 CHCA. Why is 4 being used as the MALDI derivative? And what we found out is consistently, whether it's a solution or a solid matrix, there is always the hydroxyl group, okay, as shown here. So the one that is broken line, that's the 4 derivative. The one that is a straight line, that's the 3 derivative. And in most of the cyano thing that we have here, you could see here, except for pH 1, okay? So pH 1 maybe is a lot of hydrogen there. So some of the cyano is attached to the hydrogen, okay? Because you have nitrogen reacting with hydrogen. And the one that fascinates us is this one, the hydroxyl group. So it's only at pH 14 that we don't see the hydroxyl group. So what happened at pH 14? There's no hydroxyl group because it is deprotonated. And consistently, only the 4 has peak compared to the 3 derivative. So we found out here, okay, that the presented data that we have, maybe it's because of the symmetry that allows the 4 cyanohydroxycinamic acid to be an effective matrix compared to the 3 derivative, the 3 cyanohydroxycinamic acid. We also try to use NMR for that, what we call the study to determine the thing. So the one that I did is all on the Raman, and then Jason did the NMR. And from that, we're able to come up the paper in the Journal of the Raman Spectroscopy. And then the last thing that I have done with the group, again, I just look at some of the chemicals that we have there. So I noticed this estrogen. These are hormone, okay? And I look at this, oh, I have a ketone here, I have a hydroxyl here, I have a diol here, and then I have a hydroxyl here and a triple bond. So maybe I can differentiate them using Raman, okay? And that's what we did. So it took us over a year to come up with this slot here. We have to use the big Raman because the signal is so weak, we cannot get it in the small Raman. But in the small Raman, we're able to show some differences. Okay, so this is at this region around 3000, which is the CH bond. And this is at the different region. And here we could see the one that is the ketone, it has a peak exclusively at 1751. And the one that has a triple bond, it has a peak around the 22 to 2300. Okay, but the unique and the common peak that we found is in this region. So we found out that all of them has a peak at 790. And then they have a unique peak at a particular wave number. So we are worried, is this paper going to be another assignment paper? So we said, we have to put some marketability in this paper to be accepted. So what we did is we tried to use some sort of an analytical method of it, how to determine this estrogen, let's say in an original sample or in a real sample. So what we did is we find a solution or we find a solvent when we dissolve it, we can still maintain or we can still see the common peak and the unique peak. And we're able to use dimethylformamide And what we did is we look at the intensity normalization. So we normalize the peak, the unique peak with the common peak. And what we do, we use it to get the ratio of the estrogen when we use mixture. Okay, and we're able to come up with this different mixture, and the margin of errors that we have, some can be as low as 1%, but we get as high as I think 27%. So that's the story that we came from this what we call estrogen. And then the next time that we have this is already a mixture of me doing it at PAASE and going to York College from time to time. So as I told you, I was fascinated with the cyano group. So in 2017, there's a session in ACS about Raman spectrometer, and the organizer decides to write a book chapter. And he sent an invitation to us. So I talked with Dr. Desamero. I asked him, do you want us to do some book chapters thing here? And then he said, okay, get all the data that we have, and we're going to do this thing. So we wrote, I wrote 4 chapters with him 3 on it, and he wrote 4 with 3 with me here. So we come out 5 book chapters in that book. So the first thing that we have here is we look at the different cyano material that we have, including the latex glove, the nitrile gloves that we have. And this is what we observe, okay? As the size of the materials increases, okay, there's a corresponding shift that we observe. And then we're supposed to include this one, but he asked me to remove this. So this is the different cyano with the different side chain. And I also included here some peptide. Okay. So the way that we look at this is the bigger the side chain, the lower is the intensity of the cyano group. And then we try to look at the solvent effect. So what we have here, this is a methoxynitrile. So this is an electron, methoxybenzonitrile. So this is an electron donating group. So what we observe when we put them in a solution, most of them shift to a higher wave number. But when we compare it with an electron withdrawing group, which is the cyanobenzaldehyde, the change is not as what we call pronounced as it is with the electron donating group. And included in the book chapter that we have is the an ionic liquids. Okay, so ionic liquids during that time, that's the second, we could say, popular paper behind nanomaterial. So I chose this ionic liquid because that's the cheapest that we have in the catalog. Okay, so you know, ionic liquids, this is what salt that is liquid at room temperature. So I asked my undergrad student to do a calculation in Gaussian. Okay, putting it at the different solvent in Gaussian, and then what we did is we mixed the ionic liquid with different solvent, and we found out this one. Okay, so in water, if you're going to look at the peak area that we have here, it broadens. Okay, so this means that the environment of the ionic liquid here with water is heterogeneous in nature. And it makes sense because here it's all ionic liquid, but if you mix it with the different solvents, so your environment becomes more heterogeneous. And I also look at the sol gel. So this is the reason why I was fascinated with cyano. So when I was doing a PhD, I prepared different formulations of sol gel. I was always fascinated with the cyano because it's the only one that gels at the same day. The rest would gel 2 weeks after. So it made me curious why cyano behaved during that time. So what I asked my undergrad is to monitor the step-by-step sol gel process. So sol gel is a wet chemical process that involves the formation of the inorganic colloidal suspension, which is the sol, and the gelation of the sol in a continuous liquid phase, which is a gel, to form the three-dimensional network structure. So what I asked my student is to monitor, okay, step by step by Raman and IR, what is happening to the cyanotriethoxysilane. So what we observe as we add more materials in it until it becomes solid, okay, there is an increase or the widening of the peak. So again, that is due to the heterogeneous environment where the cyano is. And the IR has the same, we could say, result as that of the Raman. So start here when it's all cyano, and when it becomes solid, it's already wider than the one that we have here. And we also use other functional group on this one. And we're trying to finish a paper of this, although this was done almost 5 years ago. Okay. And we look at the calculation, what is happening, if it's unhydrolyzed or hydrolyzed. So we expect that the hydrolyzed is an hydroxyl group, because if you have a hydrolyzed, this this group that you have there will have a hydrogen. It undergo hydrolysis. Okay. And when I have the portable Raman that we purchased for 15,000 in 2013, so I want my students to do it. Okay. So out of the things that I asked them to do it, I use them in the experiments. We're able to come up with book chapters that we have here. So the first students who did it, we have a very simple experiment. So we put benzene in a vial, and I asked her to get the Raman spectra, and then I asked her to run a calculation in Gaussian, and I asked her to compare them. And you could see here, okay, that relatively there's a peak that corresponds between experimental and theoretical results. And I asked them to do it with toluene. So I have data from the benchtop from York College, okay? And then acetonitrile. So acetonitrile, you have this peak, which is the cyano, okay? And then since we have forensic science program, we incorporate an experiment where we put a sample that contains the nitro. So this is mimicking what? The explosive. And we ask the students if there's an explosive, or this is a mock explosive in the sample. And as we go on, we use more nitro containing compound. And the students were happy with this training that they have, okay? And then one student is working with chloramphenicol, is doing GC MS analysis. So he said he wants to do also Raman. So I asked him, okay, you can do the Raman using your sample, and then you can do the calculation. And all of the what we call peaks in both experimental and calculator are usually they have the same peak in most of the samples that he ran. And I also have the calculated one from the benchtop thing. And then we use the silenes that we usually use for GCMS and IR. So we already have the handheld Raman. So I said, why can't we use them? And then when they analyze these samples using the 3 instrument, I asked them to write some sort of a pull report, okay? And one students want to do an analysis. So the thing that we do here is we use a common and unique peak, just like what we did with the estrogen, okay? So we're able to get the same results as the one that we have in estrogen. And then this is the most popular one that we have, the over-the-counter drugs. So acetylsalicylic acid, acetaminophen, ibuprofen, naproxen, or guaifenesin. So by reading this, you don't know what they are. But when you're looking, what I'm doing is you're familiar with this thing. So what I developed in an instrumental class, we have an unknown where they are going to identify, okay, the over-the-counter drugs given to them using the Raman. So I asked them to go over the benchtop results that I get, okay, see if there's unique peak and common peak, and then they run it using the portable one. So this is the portable one. As you can see, the signal is not as good as the benchtop one. So we compared the different ibuprofen, we compared the different acetaminophen brand, and I always have a kicker them when I give them Tylenol Red. They thought it's not acetaminophen, so most of the time they got wrong there, okay? And then we have the Mucinex. I asked them to look at the white and the green side of the stuff, and why the red one has this peak here. So usually the color that you have there might contribute some fluorescence in the sample. And then we have this, what we call a lid that we have here, okay? And then right now, what we're trying to do, so they use Raman to detect counterfeit for Viagra. So this is the original one, and this is the fake one. So look at the fake one. There's some additional fakes that you don't see in the original one. And then we also use the Cialis here So you could see the counterfeit, okay? They have additional peak, okay, compared to the original one. So I was in the Philippines in 2018, and my pharmacist gave me not enough metformin. So instead of 45 metformin, he gave me 30. So out of the sudden, good thing I can buy over-the-counter metformin here. So when I come back, I have some samples that I told my students, can you analyze it? So I found out they're okay, except for this one here, okay? But the rest of the functional group, they seem to be fine. Okay, and I think the company where the metformin manufactured is a little good one. So I asked my student to analyze that one, and some of student mine. So the same thing that I asked them to do, group assignment and look at the difference. So this is benzoic acid derivatives. Okay, so the one that is changing is the substituent in this ring, and then the fumaric acid here, or the cinnamic acid derivatives that we're almost finalizing, hopefully by this semester. And then I have some antibiotics in the lab. One student's work on it. Okay, so this is the portable one. This is the benchtop, and then another students did the sulfa antibiotics. So I asked her to compare the 5-member ring compared with what we call the 6-member ring. Okay. Now, the future projects that we have, Jason left me some samples, poop turtle, coming from a professor in Hofstra, and he asked me to continue to determine the microplastics. And since we're near Chinatown, okay, we try to look at these, what we call counterfeit drugs. Okay, so you know China, right? They say if it's not made by God, it's usually made in China. Okay, and then I have student from UP Diliman who did part of her MS thesis. He brought me some seafoods. So we tried to develop, using the portable one, food authentication of quality. So we have here tilapia, different process. So we try to see, does this really make sense? Okay, so we might use a little bit powerful Raman. So I'm thankful that we have this thing so that I can start doing my proposal to purchase a Raman, because this is the UP student who worked with me. Now that black curtain there, okay, there is an old Raman spectrometer that I got from a private company, but unfortunately Horiba don't want to install it. So I might be forced to apply for the NSF MRI grant to purchase a Raman spectrometer. Okay, so that room can be utilized. So the members who did the Raman here, all of them are ladies. So Claudia Sobolowski did the initial one. Some did the sol gel. Tabitha Bate is a PhilAm, okay, who's doing a PhD now in Northeastern University. He did the Chloramphenicol. Nadia Abbas did the ionic liquid. Alexis Yabornik, who's now in forensic science in Texas, he did the sulfa. Ashley Capsor, a PhilAm also from Philadelphia, is now with NYPD. He did the fluoroquinolone. Some did the some patient again did the phenolics. Jahaira Zapata completed the over-the-counter analysis, and then over-the-counter drug analysis. Lauren Riley did the Silene. Lyric Wyan did the Cyano, and Elise Crapso did the Metformin. But I think everything I owe is to this guy. We call him the big boss here in your college, Dr. Ruel D. De Samero. And I'm happy to recruit Jason Di Bedad to be his PhD student. So Jason is now in Union College here in New York State. And the lab is now headed by Marvin M. Bilog. So the lab, we usually have some visitor like Professor Myla Santiago from UST. We have some undergrad students who did some research with Dr. De Samero lab. So he had also a black curtain there in his lab. Okay. And then we also have Dr. Frank Heralde from UP Manila. And I think he will be sending some of his students to do some research in the near future in the Samero lab. So we're happy to say that we have a MAPIA, at least in CUNY CHEM. So these are the students coming from UST and UPLB. So that's our bossing here. And then that's me there. And I'm glad that Kay invited me to do this thing, because for the last 2 months, I've been giving webinars to prepare our teachers there for the pandemic. Okay, so I think I have already 16. This is the 17th webinar, and I'm thankful for UP Visayas Department of Chemistry because they allow me to guest lecture in an instrumental course, and one of the topics that I have there is Raman. Okay, and all of these webinars, some of them, if you still don't know what to do for the pandemic, you can see it in my personal webpage. In fact, I have a webinar by 10 o'clock after this in Cebu Technological University. So thank you very much. I hope you learned something with what I have done in Raman Spectroscopy. Maraming salamat po.
Thank you very much for that, Elmer. It was a very interesting presentation, and I hope that some of our audience would take interest, especially for those who are not yet into this kind of research. Okay, so now we're open to questions. So again, for our viewers, you may type in your comments or questions in the chat box. And for those watching on YouTube, feel free to just type in the comment section, and I will be reading those questions as well. Okay, we have our first question from IC Duay. So, Elmer, that was an interesting story on the amyloid peptides. Did you try looking at the final size of the modified amyloid peptides with slow aggregation? Or are these comparable with the size of the native amyloid peptide aggregates?
So this is the story of that amyloid peptide. What I did is just a scratch in the surface thing. Okay. So what happened there is when Jason Bedard took over, he used those peptides that didn't aggregate. He mixed it with the amylin, what we call peptide, and he found out some of those octapeptide, as we call it, were able to inhibit the amyloid formation of the amylin. Okay. So the one that I have is, we could say, I just did the beginning, and I said, Jason, bahala ka na dyan. It's up to you. Okay. What Jason did is he prepared other what we call peptide using the NF-GAILSS, and sometimes he is stretched. He include the SN NF-GAILSS, and we're able to find out. I was still part of it, but I don't want to talk about it because I never really what we call participate in that deliberation on what they said. But there are papers of Jason Bedard with Dr. Desamero that describe how they were able to prepare these peptides that was able to inhibit the amyloid formation of amylin.
Thank you. The next one comes from Janet Morata Fuentes. So thank you so much for that interesting talk. Would you be aware if there is a Raman Spectro in the Philippines? Is anyone using it?
This is what I'm aware of. I think there's one in UP Manila. I just forgot the name. And I don't know if Dr. Erwin Enriquez already purchased the Explora, because Dr. Erwin Enriquez, who is a contemporary of Dr. Desamero, he visited us here during the 2017 when I delivered a ACS in Washington. And then I found him in Washington, and I told him, why don't you go to New York? And they said, oh, we're really going to New York. And then I said, oh, you might know someone there, Dr. Desamero. And they said, yeah, he's a contemporary of mine. And they talked, and I think, I'm not sure. I have no contact with Dr. Enriquez except today when I invited him to the seminar. But the last time he emailed to us that he's planning to purchase Explora Raman spectrometer. But that's the only people that I know. There's a Renishao Raman in UP Manila. I know it because I read the paper in Philippine Journal of Science about Raman spectrometer.
Yeah, maybe just a follow up on that question. So I know that you've been engaged with a lot of Filipinos and a lot of scientists from the Philippines. In those engagements, have you already explored? Have you explored what collaborations have you done with some of our scientists regarding this Raman spectroscopy?
I'm part of the 20 million. What do you call this? Picari UP PCHRD grant there. Unfortunately, the head of the grant, Alonso Gabriel, passed away this year.
Okay.
And
Yeah,
we're
yeah.
not done yet with the project. And unfortunately, Raman is not included there. But what happened, he was able to send one of his master student, the one who worked with me in the lab, but he's doing this seafoods thing. So it's not ramen related. So what I'm doing with that project, we're working on breast milk, and he asked me to analyze for the heavy metal content and what we call fatty acids. So we're not done yet because right now my lab is shut down, and I have no plan to do any research for the fall semester because I said 1 week, 1 day a week is enough for me to show up because I have some comorbidity that if I get the COVID, I might die. So that's the thing that right now that we all we do right now is just look at the data that we have and
Mhm.
see if we can come up with some papers. So that's just one of the, we could say, funded project that we have. I also have some collaboration with a friend of mine since I was in the Philippines who was in CHED and then went back to PNRI. Okay. And then I have some friends in the B program. So they sent me some propolis sample. They asked me to analyze it. So some of my students do it. But the thing is, the undergrad that we have here is not the same as the undergrad that we have there. Because the undergrad here, not all of them are required to have this thesis. Only the honors thesis are the one that is required. So I cannot rely on my undergrad. I can only rely if they're honor students because they need to come up with a product, which is a thesis, before they complete the degree. So that's why what happens is sometimes it's all me who doing the thing. So I ask them, then sometimes I ask another student to validate the results of the other students, and they're good. That's the only time I said, okay, let's publish.
Okay. So, but are you open to accepting any future students?
Yeah. I mean, usually I have a network already with
Okay.
UST. I'm not sure if Sir Gardi is there, the chair of the Department of Biochemistry.
Okay, that's good to know. Okay, and a few questions from Vince Daria. First one is he noticed that you were able to detect very small shifts, for example, from 1608 to 1605 centimeters. What is the noise level and detection limit of the Raman setups? And the second question is, do you have an overarching scientific question that puts all the pieces of your results into proper context?
So the overarching that we have there is, can we develop inhibitors by using fragments of the peptide? Okay, that's the original plan that we have. So can we take some of the fragments, synthesize them, and we mix that fragment with the whole peptide? Can we prevent it from aggregation? That's the main art of the story that we have. It's just developing inhibitors based on the fragment. Okay. And right now, Marvin, are you there? I know what the students that's doing it. That is the same story that we had. So he had some fragments, and I think the one that they do is an SAA because as much as possible, I don't want to what we call the venture on the amyloid, the one that they do by this America, because the one that I do is different also in my lab. The one that I do is I use the natural product phenolics to see if I can inhibit the amyloid formation. But for them, when we started doing that thing, when I was still part of the thing, is we try to develop inhibitors using fragments, okay, of the amylin. So we choose amylin because others I think is the alpha beta peptide for the Alzheimer's disease. So they use the same concept that we use. I think that's the basis why we started this project. Okay, and for the ship, it's one wave number for the signal to noise. There's really a story that we have there because usually we have some problem in the structure that we have. The building is near this LIRR train, so every time I make it my SOP that every time we run the instrument, we run this toluene. And we always record where is the peak of the toluene. Because I remember, I think after 3 years, I said, oh, there's a ship. And then when I realized that the toluene also shipped, I just told the summer, oh, don't mind. I just need to do it again. Because we said, this is false alarm. So we always run this toluene as our standard to see if the instrument is always aligned. Especially in the big Raman, it doesn't have a standard. Like we're the one who have to find where we need to put the line. Okay? And Jason was really good on that thing. Okay? That's why when I saw that he was able to get a signal that is 1,000 or 10,000 times than me, I always said, can you prepare the big Raman for me when I go there? Because I usually teach there once a week. And whenever I go there, while I'm teaching lectures, some of the instruments are running. So I'm taking advantage of the time that I have there. Because I don't have that high-end instrument at Pace University.
Okay, I think Giselle is raising her hand. Giselle, would you like to say something? Hi, Giselle. Yeah, but we can't seem to hear you. Giselle, I think your microphone is off. Yeah, we can't hear you. Yeah. Okay, so while we're waiting for Giselle to respond, so let's just go through the next few questions. This one's from Ray Ranyola. Are you familiar with Raman mapping and what are the uses of it?
Raman mapping, I think, if I'm not mistaken, is if you have the microscope one. So I never use the one on this, what we call the microscope one. So the way that you try to do it is just like when you look at the microscope. So you have a map there, and depending on the concentration or the functional group that you're looking for, you will see like a map that you have there. And that's the one that I'm trying to apply for this NSF grant for next year, a Raman microscope, which is a little bit lower than the one that I shown, Explora type. That's the one that we're trying to do. So I never used the Raman mapping, unfortunately, in my Raman experience.
Okay, thank you for that. So the next one comes from Marianette Vega. There is a home-built Raman system in NIP, Condensed Matter Physics Laboratory of Dr. Sumintak, Dr. Estacio, and Dr. Salvador. Are you familiar with that?
Unfortunately, no. But Dr. Salvador is familiar. If that's Arnel Salvador.
Yeah, and if
Yeah.
this is Dr. Elmer Estacio, we're actually having him next week.
Okay.
So maybe we can learn more about that next week. Okay, so the next question comes from John Pimentel. So he's from Colombia. So he would like to ask, do you think it's possible to employ Raman spectroscopy as an inline sensor of concentration for the industry? Are sampling times and accuracy suitable? And the second question is, how can the accuracy of Raman spectroscopy be enhanced?
It depends on what sample you want to analyze. So if your sample is not fluorescence, I think there are already what we call portable Raman, like the one that we use. The one that I use, they're still much smaller than that one. And depending on what we call, I mean, each of them has their signal to noise ratio. And to tell you frankly, Dr. Desamer would always laugh at my portable Raman. I said, I don't believe in that portable Raman of yours. The signal to noise is really low. And you could see it from the thing. But I said, I don't have any money, so what can I do? At least I have something to do here. Okay, so it depends on what application that you can do. And there are usually available what we call Raman. Most of the time right now, the Raman spectrometer are already portable. So we're waiting for the DEA, the Drug Enforcement Agency, because they said they're purchasing portable Raman. So they're going to give up the benchtop Ramans. And we're hoping that we can get it. Because usually we get some hands-me-down instrument from them. All we know is we have some what we call clinical faculty who's teaching in our MS Forensic Science. So whenever we said, oh, we have some instruments that we need to dispose. Do you want this one? So we're able to get a lot of GC, GCFID and GCMS. We're able to get HPLC. So we're hoping that right now, if we have a Raman, we're willing to take the Raman. Yep.
Okay, thank you. Yeah, so maybe we'll see more developments on the instrument in the coming years. Okay, I think, Giselle, are you back? Yeah, Giselle, can we try your mic again?
Yeah, sorry. Can you hear me
Okay,
now?
there we go.
Sorry,
Yes, yes, yes.
to my cell phone. So Elmer, congrats and thanks
Thank you.
for helping so many. And wow, it's a full audience, and I even see Leslie Diaz of UP Engineering. So wonderful. First is have we invited Dr. Desamero as a PAASE member? Elmer, first
Uh,
question.
this is the thing. I know you know Jin Chong, right? They are contemporary of Jin Chong.
Wow.
I always ask him, "Can you join?" I said, "No, that's not for me. If you want, you can."
Well, now it's different because we're more interactive. You know, wow, it would be great if we could have him join us and he sees our webinars. No, so well, my own interest is in this peptide fragment that looking at as a possible inhibitor, and we know that what's critical would be the 3D structure of any peptide. Well, does it mimic the native peptide? So, to what extent would Raman help with, the 3D structure? And of course, well, you're using it for known compounds mostly, so it's analytical, no? Pero, syempre, our challenge here is to discover new compounds. In my case, from marine sources, and now I'm also looking at plant. And so naturally, we would always want spectroscopies that could do absolute configuration. And well, if it's a peptide with the amino acids, then you just want to do also DNL. So we have a master's student who recently defended, and the determination of the D or L is still indirect, and it is just based on illusion from the HPLC. So there's always a challenge. So even in UP Diliman, we don't have the appropriate ODC-RD yet to measure small quantities of peptides and the
Yep.
micro or nano quantity. So I think I'm trying to ask how it is that you would use Raman, because we don't normally use it,
Yeah.
okay, for to help us in drug discovery, okay, and not just um, you know work on compounds that are already known. Okay, in the case of your peptide fragment for diabetes, its absolute configuration is already known, but you still want to know what the 3D might be, right?
Yeah.
Okay, so that's my question, Elmer. Thanks.
Thanks, Ma'am Giselle. So to tell you frankly, Raman is just one of the tool. So when we do, let's say the amylin study, we use other spectroscopy. Okay. Uh, in fact, the thing that Dr. Desamero was happy to me because every time I'm in the lab, all of his instruments are running. Because the ratio that we have in the lab is he had more instrument than people. So whenever I go there, the UVBs is open, the spectropolarimeter is open, the Raman spectrometer is open, the CD is also open. Because what I do from one cubet, I just put it to the next instrument and then the next instrument and then the next instrument. So Raman is just one of the two. It's not the only tool that we use when we did the study. And each of the tool has its own purpose. And to tell you frankly, I know, Ma'am Giselle, you know Frank. Frank stayed here at our place for a week asking me to train how to synthesize the peptide in Dr. Desamero lab. And Dr. Desamero, yes, you can train him, but you will be the one to train him, not me or any of the PhD students that we have. So Raman is not, we could say, is applicable for something. So the one I think that it can do it is you are looking at some novel compounds coming from the marine organisms. So the question that I will ask, how do you test them? Is there any changes that happen during this testing? Because Raman can monitor those small changes. So I think that's where a Raman can be used for application. Because for us, we just monitor it. Oh, there is what we call a beta sheet. And I remember in one of the review, one of the when we submitted the paper, one of the reviewers said, "Have you used IR?" So that's why we said, "Oh, this guy doesn't know anything about Raman." Because usually, if you have the IR, whatever information the Raman gets can be supplied by the IR. But it's much better if you have both of them to complement one another. So I think that's the reason why Raman is not really a popular method. Okay, it's more expensive than the IR. IR here, as early as organic chemistry, students can have access to IR. That's just the way I look at it, Ma'am Giselle.
Yeah, thank you, Elmer. And Dr. Desamero's lab is open.
Yep,
So you're not
we are
the lab.
always open. I mean, the way that we do it is we're willing to host students who want to do their PhD. I think Dr. Enriquez promised us to send his PhD student, Dr. Erwin Enriquez, and then Dr. Heralde said, I think one MD PhD in the MD PhD program will be sent originally this December, but because of the COVID-19, I think there's a little bit of delay. Because what happened, whenever someone applied to him, he will give it back to me. And then he said, can you get a background check of me? Because my role, I always said, I'm the liaison officer in the group. And sometimes if the students have problem going here, I'm the one that I ask them, do you have any problem? And usually I always tell them, if you work in Desamero group, you only don't get one recommendation letter, you get two recommendation letter. I'm the one who will give the other recommendation letter, as what Dr. Piedad, when she finished, did. So we're always open, because the thing is, we just hope that the one who will come here will really work, because that's the way that we want. We want people to run some of the instruments.
Well, thanks, Elmer. I just wanted to tell you what we are able to do already in UP Diliman. And Frank obviously is not aware that we are synthesizing milligram quantities of peptides. So we have many conopeptides and turipeptides that we have synthesized in the lab of our collaborator, Aaron Villaraza of Institute of Chemistry.
Oh, I see.
We are, during a Liberty Blue peptide synthesizer with much greater capacity. So, so we have NMRs in UP Diliman, as you know, a 400 and a 500. And I think De La Salle has a 600. And then we have mass specs and LC mass spec, tandem mass spec. So these are functioning by and large in UP Diliman, except that, like most of us, they're on lockdown now. Okay, so there's very limited access and activity because of the COVID. So I think, we're kind of getting there. I checked Erwin Enriquez of Ateneo. Yeah, he's a leading guy in Ateneo. But I didn't see any Raman instrument yet in the Ateneo website. Okay, but yeah, these are good guys to train, and people from their labs would really work very hard in your labs. So thanks a lot, Elmer. Thanks.
Welcome po.
Okay, thank you. Our next question comes from Rosa Teresa Albano. Have you explored Raman studies for materials that can be used for biomass or as recycled materials?
No, unfortunately, no.
Not yet. Okay. Have you encountered any studies on those?
No, not yet. Because right now, all of us, even his lab, only I think Marvin is the one going to the lab.
Okay. The next one comes from Leslie Diaz. So can you explain a bit further on how gases are measured or tested using Raman? And can the Raman be also hyphenated to the thermogravimetric analyzers, such like the FTIR? It is interesting to note that transformations of a molecule can be monitored. Can this be done in situ? What is the concentration limit of detection?
So with regards to the gas one, so the way that we try to do it is we usually heated the sample so that it will volatilize into gaseous spacer. And what we do is we just hit the probe on that thing, and sometimes we're able to get it if there's enough sample in gas. I mean, if there's enough gas sample that we have here. We also do it with IR. Now, in terms of hyphenated, I have not heard anything about Raman being hyphenated because I think it has something to do with the nature because you have to hit a laser to it so that the scattering process will happen. And with regards to the detection limit, I think it depends. The more portable it is, the higher the detection limit. So that's the problem that they have with this detection limit. But what I know is every year there's always an improvement. The mini RAM that I have from BW Tech, it's not available already in the market. Okay, so what they have now is the nano RAM, and I think Dr. Advincula, Gobet Advincula, has those stuff in his lab using for polymer study. Okay, so with the advent of technology right now, I think every year the company, they always email me, oh, we have this new one, but I said I don't have no money for that one by this time. So it's keep on improving. Okay, and the thing that we have right now is everything to be done remotely. And even my students who are in the drug enforcement agency already, they said they're thankful that we have a portable one because that's the one that they use right now in crime investigation.
Okay, thank you. That's really interesting. And then we have the last question from Dr. Dilip. So, in a sample analysis, what are important about the ID IG value?
I'm not familiar with the IG value.
Yeah, me as well. Sorry. Okay.
Sorry, it's the first time I heard that thing.
Okay. So yeah, so maybe he can get in touch with you if he would want more details about his question. Okay. I think we've exhausted all of the questions. Elmer, do you have any final words for our audience?
I just like to say hi to my MS advisor, Dr. Florinia Imerca, who's attending right now. One of my BFF in science, Castor Jokaris, was also, I asked him to attend because I told him, I'm doing something that you might not know. So I know his imagination is really what we could reach. And maybe by tonight, we'll be chatting again, and then he will say something about a particular thing. So all I ask you is, I'm willing to help you, if not in my lab, maybe in Dr. Desamero's lab. But the only thing that we have, because we're a little bit disappointed with some of the things that come here. I think most of them are this YOLO thing. You only live
Oh,
once. Because I always tell them, all the statue here in New York City will always be there. And I always tell them, in fact, not all places in New York I have visited already. I only visited those places when I have some friends who come here. Okay. My wife and my son is the one who have visited more places than me. So we are willing to do this. I'm open to collaboration, but though I want to finish first the one that we have with Dr. Alonso Gabriel.
yeah.
So I'm not sure if her student is here because I'm pressured to produce something out of it. Unfortunately, we cannot do with the pandemic. We're limited with time because the rule that we have, if we want to work on the lab, you have to develop a protocol. And as I said, I'm not going to do that. I'm not going to put myself in those situations. So
Yes.
that's the thing. So we're hoping that when the pandemic is done, we'll be back to what it is during that time.
What about your talk at 10 o'clock? Is it open to everyone?
It's organized by Cebu Technological University. So the way I ask them to do is, you give me an audience and I will do all the talking. So I think I have around most, I don't know, because I was a speaker in Bibal in Facebook. So I'm happy that I was able to share what, because I have two sessions, spring semester and summer session. I taught full time, and right now it's the third time, and it's getting worse in terms of the stress level. We're already 2 weeks from the semester, and we feel like it's 2 months already, and we have
Yes.
not done face to face yet. We start doing face to face next week. But we're hoping that everything will be done, but it will not be the same as the old ways. So that's
Mhm.
the problem
And
that we have.
so we'll check all of your lectures in your website. But before we go, I'd like to share with everyone. So again, a bit promotion. Okay, so thank you very much, Dr. Elmer, for sharing with us your research on Raman spectroscopy. So next week, so his name actually came up in our Q&A. So we'll be having Dr. Elmer Estacio from, who is a professor at the National Institute of Physics at the University of the Philippines. So he will talk about the generation of pulse terahertz radiation in semiconductor materials and antenna devices using ultrafast laser excitation, theory and application. So we're doing it again on a Friday at 8 o'clock in the morning for those of us here in the Philippines. And if you're interested, please register at bit.ly/eestacio. And again, the Philippine American Academy of Science and Engineering. You can find us on Facebook in our official Facebook page. We also have our website, which is paase.org. And the webinars that we are conducting, we upload them in our PAASE webinar channel, which you can find at bit.ly/paase webinars. Okay, so I guess that ends our session for today. Thank you very much, Elmer, and maybe we'll invite you again to talk on
Fine, it's
other.
okay.
Okay, so thank you so much, everyone, and I hope that you have a good weekend for those of us in the Philippines, for those in the US. So good night, and see you again next week.
Okay.
Bye.
Bye.